is a so-called Horner's method for polynomial evaluation. All right, so the idea is that, well, we need to evaluate polynomials, right, in the computers. And even if we don't have polynomials, we use polynomial to approximate a function, right? I hope you understand the importance of polynomials, right? We do interpolation. We're using, or Taylor expansion, we're using polynomials to approximate an unknown function, right? Which is a great approximation, and if the interval is small. And so evaluating polynomials efficiently is important. Say we have a polynomial of an x to the n plus an minus 1, x to the n minus 1 plus z, right, all the way to a1x plus a0. A0, okay, A0. All right. Think about how we evaluate it, right? So option 1 is probably a most naive way, which is for any I, right? For any given I here is from 0 to n. We compute x to the I, right? And then we compute ai times x to the I, right? And then add to the sum, right? Which is 0 to start with. Okay, basically, I'm saying, so yes, a better option is that I record x to the I, right? When we need x to the I plus 1, just do x to the I plus 1 is equal to x to the I times x. All right, times x. Okay. We're going to have n additions, right? N additions, and how many multiplications? We have 1 plus 2 plus all the way to n. That's an x to the n multiplications, right? And i.e., how do we add them up? You can all do that, right? N times n plus 1 over 2 multiplications, right? The second option, you still have n additions, right? You just add to the existing sum. For each term, ai x to the I, we only need to do, we multiply with the previous x to the I, and then we multiply with the coefficient ai. How many multiplications? For each term. So yes, that's 2 times n multiplications, right? So that's already way better because we go from n squared to n. What's nice is the following approach, right? I mean, basically, we're already linear to n. You can never do better than linear because you need to, at least you need 1 for each term. You can never do better than linear. But can we cut that 2 down, right? The answer is yes. So the key is the trick. The trick is that I'm going to rewrite f of x. Look, this smart this trick here, right? I'm going to do a an x plus an minus 1. That's my first operation. I take my x and multiply with an. I add an minus 1. And then I'm going to multiply with I take that as my existing sum. I multiply that with x plus the next coefficient, an minus 2. And I multiply that yet with another x. Now I take the whole thing as my new sum, x plus an minus 3. And yet outside x plus an minus 4, so on and so forth. Again, you know, if you were to write a little pseudocode, right? You start with one guy. You start with your current sum. Your sum is equal to an, right? What you do is that for a loop, right? For I is equal to 1 to n. What you do is that your sum is equal to sum multiplied with x plus an minus I, and that's it. You take your current guy, you do the same operation every time. You multiply with x, add the next coefficient, multiply with another x, add the next coefficient. You do this n times, you're done. So again, amazingly, we'll need, this is the only loop, right? We need n additions and n multiplications. We go from 2n to n. All right? That I want to talk about is that we went through very quickly at the time, but when we talk about the orthogonal polynomials the other day, when I found out you had some errors, I think that, right? So from 1x, x squared, x cubed, all right, and we move to 1, right, x, right, and then the next guy is you start with x squared, right? You subtract its projection onto each of the previous guys. Okay? I subtract this onto 1, the projection onto 1. How do we do that? We take the inner product of x squared from -1 to 1, right? 1 times 1 dx divided by the length of that, right? That's squared, 1 squared dx. That amount of 1, right? And then subtract this guy, x squared, onto x dx divided by the length squared of that basis. That amount of x, right? So we're going to get, this is x squared minus, so that's x cubed over 3, right? 2 over 3 divided by 2, you get 1 over 3, right? So that's why it's x squared minus 1 over 3. Okay? And it's x cubed is, you do that, you subtract this, you subtract its projection onto each of those 3, right? Each of those 3. But you don't need to do this and that because you're going to get an odd polynomial. Okay, so they will disappear. So you'll need to compute x cubed times x dx divided by x squared dx. And don't forget about multiply by what? X. That's a very common mistake. When we did, so this is equal to x cubed minus, we have x to the fourth, right? Which is what? X to the fifth over 5 from -1 to 1 divided by x squared, which is x from -1 to 1, right? So that amount of x, again, don't forget about that object. Object minus this object onto the previous objects. That's only give you a scalar, that amount of the previous object, right? So we're going to get what? What's that? 2 over 5 divided by 2 over 3. So that's going to be x cubed minus 3 over 5x, right? X. All right. So the Gram-Schmidt again is such an important procedure. It's not just to vectors but to functions, and any objects as long as you define inner product. You know, a voice or an image. So it's really important to know, right? But that's not what I'm trying to talk about here. It's something that we listed that basically says that the endpoints, right? The endpoints, you get, the best case is that you get 2n minus 1 degree of exactness for integration, right? Integration. And that endpoints, these endpoints should be, you know, if we call this guy, this is like our L3, L2, L1, right? Around the polynomial, as we will talk about, they should be the roots or zeros of Ln. Okay, Ln. E.g., for example, all right, if we look at x squared minus 1/3, we let that to be 0, which give us solution is x is plus minus square root of 3 over 3. Which means if you only put 2 points, right? So 2 points. This is only on the reference interval from -1 to 1, all right? On -1 to 1 should be, you know, not the 2 endpoints, not the 2 middle points, not the as in the Newton codes, just put uniformly distributed points, but you should be smart and put negative square root of 3 over 3 and then positive square root of 3 over 3. Okay, so that's power of this one particular application of the orthogonal polynomial. With 2 points, it will give you 2 times 2 minus 1 is 3. You can do a cubic polynomial integration exactly. Okay, that's power here. If you put the 2 endpoints, -1 and 1, remember, what's the degree of exactness? The trapezoidal rule, right? It's only one, right? If you are smart enough, you can go from 1 to 3. You can integrate a cubic polynomial exactly. That's one particular application, right? And to get there, to get to the conclusion, why do we have that? That was theorem that we only wrote down but didn't prove. All right. To get there, what we need is that theorem that we wrote down again, but I want to prove part of it today to finish. So the idea is that for what we wrote down is that for the degree of exactness, again, because it's Gaussian quadrature is so important, and the tool, the orthogonal polynomial is so important tool. That's why we are revisiting this, right? So for the degree of exactness to be m plus m, right? M points. If and only if IFF means if and only if. That's exactly the same as we wrote down last time. It is interpolation, interpolatory type, and that -1 to 1 of the omega m plus 1 of x, px is equal to 0 for p of x is a polynomial of degree m minus 1. All right, that's what we wrote exactly to be m plus m using m points. This again basically just says that the weight alpha I is integral of your Lix dx. All right, the Li of x is summation product x minus xj, j from 0 to n, j is not equal to I, divided by the same guy, but evaluate at xi. The characteristic of polynomials, okay? Questions? So I'm going to prove that it is sufficient. Means that if it satisfies these two conditions, then it has a degree of exactness m plus m. That's what sufficient means. All right? So that means if f is a polynomial of degree m plus m, right? So the goal, right? The goal is that I need to prove f to be any polynomial degree m plus m. This means that it is a polynomial of degree m plus m. All right. Then my integral of f of x dx, right, is exact. Is exactly a summation of alpha I f xi, right, xxi. Okay. The idea is to do the long division that we talked about, we used last time, or maybe 2 lectures ago, right? So if f is such a polynomial, then f of x can be written as omega m plus 1 x. Remember that omega m plus 1 is x minus xi, right? I from 0 to n. Okay, I from 0 to n. So I have a typo. It's m plus 1 points. It's only all relative. If we divide this polynomial by, if we divide f by this omega m plus 1, then we're going to have a quotient plus a remainder, right? A quotient let's say pi of x plus a remainder, which is some kind of q of x, right? This is a quotient. This is the remainder. Marco, why you shake? As we were doing last time. If you are dividing by x cubed plus x squared plus, 3x plus 1 divided by x plus 1. So this is our quotient. What we have here is our quotient, which is if you do x squared, you're going to get x cubed plus x squared, right? And 0, you need to move 3x plus 1, and plus 3, you're going to get 3x plus 3, negative 2. So that's the remainder. Okay? So this, in particular, this guy is m minus 1. This guy is n. Right? Okay? So the qn of x, this is at most degree n. Degree n. Which means I use n plus 1 points to do a degree n interpolation, numerical integration. That's exact. Right? That's one result that we have. The degree of exactness is at least n when you have n plus 1 points. With 2 points, the degree of exactness is at least n. So qn of x, this can be integrated exactly. Again, if it's interpolatory type, this means that the degree of exactness is at least n. At least n, because you generate that. You generate the polynomial, right? You reproduce a polynomial. Okay. You reproduce polynomial with 2 points. You reproduce polynomial degree 1. So if you start with the polynomial degree 1, then your interpolation is itself, of course, the integral is exact. All right. For any given such f, once we do the long division, the integral of negative 1 to 1 of f(x) dx, this is the integral of that omega n plus 1 x pi n minus 1 x dx, right? Plus the integral of qn x dx. By the condition, we're proving this sufficient. So we know the condition start with, we know this is 0. That's the condition. Plus, and qn is something that we can integrate exactly. So we know that's exactly equal to summation of r of I qn at xi. Right? That's what we mean by exact. The first guy is 0, that's condition. Okay? And what is qn xi? That's just f at xi. Because if you evaluate at xi, f at xi equals this at xi, what is omega n plus 1 at xi? 0. It's x minus xi's. So the reason f of xi is equal to qn xi, that's because the omega n plus 1, if you evaluate at xi, you get 0. All right? So the fact that you can integrate q exactly means that this integral is nothing but that, alpha I qn at xi. That's what we mean by exact, degree of exactness. Okay? And it happens to be qn xi is equal to f xi. So if you look at if you look at what we started with and what we ended with, this is equal to that. That means f can be integrated exactly. Right? There's no approximation. Okay. So let me write that down. The fact that we need to make this guy 0 is that the observation from this condition, we need this condition for that high degree of exactness. As we just discussed, the observation is that if omega n plus 1 of x is a Lorentz polynomial of degree n plus 1, it's a polynomial. We know it's a polynomial degree n plus 1, but what type of polynomial is up to how you choose the points. If you choose the points to be the zeros of the Lorentz polynomial, then it will be Lorentz polynomial of degree n plus 1. Then the pi n minus 1, that polynomial, that quotient, can be as high a degree as n, right? Because Lorentz polynomial degree n plus 1 is orthogonal to any polynomial degree n, which means n minus 1 is n, so m is n plus 1. So what we concluded is that using n plus 1 points, we can have n plus m, which is n plus, our m is n plus 1 degree of exactness, right? So that guy is 2n plus 1. 2n plus 1 is equal to 2 times n plus 1 minus 1. Right? So, which means using, if we do m points, if you do m points, that will lead to 2n minus 1 degree of exactness.